So let us now talk about enthalpy changes. Before we start our exploration of enthalpy, we must define what we mean by a system. Now, in science, we sometimes use system to describe a series of interacting objects. In physics, for example, we refer to open and closed systems. Closed systems are disconnected from the rest of the universe. Things like conservation of momentum apply. Whereas in open systems, there's interaction with the outside universe, and we have external forces accelerating or decelerating an object. Now, a system in chemistry is a series of interacting chemicals. And basically what's going to happen is we can set up the same situation where the system is the particular chemicals we're talking about, the surroundings, everything that is not in the system, sometimes called the environment. Together, the system and the surroundings make up the entire universe. You're either in the system or you're outside of it. Now, what is in the system? Well, first of all, the reactants and the products. We might have a reaction where the reactants turn into the product. We might have a reaction where the reactants slowly turn into the product, and at a midpoint, there's an equal amount of reactants and products together. It encompasses the physical state of those chemicals, and importantly, it is important for us to consider the energy changes that occur. So when we talk about heat and light, we talk about it perhaps moving within the system, or we could talk about it leaving the system and going into the surroundings. Now that would be an open system. If energy is coming in and out, that's an open system. Closed system is when there is an exchange of energy but no matter, and an isolated system where there's no exchange of matter or energy and everything stays within the system. So what is this thing called enthalpy? Well, there are more than one way of looking at it, and from your GCSE knowledge, you might be slightly confused. It's a capital H, the symbol, and it actually stands for the heat energy. If you remember from your GCSE physics, heat was the transfer of thermal energy from one place to another. And actually, what enthalpy is a measure of is the amount of heat energy per mole, the amount of heat energy that each mole of chemical could release due to the breaking of its bonds. So in some situations where there is a release of heat, it is exothermic, and we'll say that the enthalpy has gone down. It's less than 1, and that's because the system is losing its heat to the environment. Yes, we detect a temperature rise because the actual chemical is losing its heat, so the change in the enthalpy is negative. If it absorbs heat from the environment, the change in the enthalpy will be greater than 0. It'll be positive because the system is gaining and the environment is losing. And so that is why we often equate the enthalpy or the change in enthalpy to the heat energy being exchanged with the surroundings. But commonly, we also refer to enthalpy as the energy stored in bonds in a particular chemical substance. Now that's true. Chemical bonds are basically a store of potential energy. It's due to the electrostatic attraction, and if you want to move those two atoms away from each other, you've got to do work against that force. And so basically you have to put in energy to separate those atoms away from each other. And so if you look at the diagram below, we're putting heat energy in, we're separating the two atoms and breaking the bond that exists between them. Now that requires energy. That's an endothermic process to move those atoms away. And of course, what happens when they get close to each other, they come in range of each other's electrostatic attraction and they click together, almost a little bit like magnets, I always imagine. And in the process, they give off some heat, like the sound of the clacking magnets as they hit together. So the enthalpy change of the reaction depends on the difference between the energy required to break the bonds and the energy released when new bonds form. So how is enthalpy both heat energy and the energy required to break bonds? Well, it is. We just need to think about it. So if we were putting energy in to break bonds, we have to put the energy in some way. It has to be transferred to the chemicals somehow. It is transferred in the form of a heat energy transfer. And what happens is, what the atoms do with that energy is they move further apart from each other. And in doing so, they then break the bond. Now, if they were to come back together, that snapping together of the bond has got to release some energy, and that would be in the form of a heat transfer, also, in this case, coming out in the form of an exothermic reaction. And you can see on that diagram there, the individual atoms are snapping together and some heat energy is coming out. So enthalpy is both the stored energy of the bond and the heat energy exchanged during the reaction. The most interesting thing we could measure is the change in enthalpy, which is to do with the heat of the products minus the heat of the reactants. It's just the difference between what has been formed and what there was originally, to find out what the change has been, because this change could be both positive or negative. There we have an endothermic reaction. The enthalpy of the system increases and it takes heat energy in to do so. In an exothermic reaction, the enthalpy of the system decreases and it gives out heat energy in the process. At GCSE, you would have seen diagrams like this, but did you know? These are called enthalpy profile diagrams, and this is an example of an exothermic one. So on these diagrams, we draw the enthalpy on the y-axis and the progress of the reaction on the x-axis, akin to time, I suppose. Now for this exothermic reaction, the reactants have got more enthalpy than the products. And in order for it to lose energy in the form of an exothermic reaction, it has to basically, the reactants have to decrease in energy as they become the products. The delta H, the change in enthalpy, is negative. And the difference in the enthalpy between the reactants and the products is how much energy is released via the heating that comes out of this exothermic reaction. Endothermic reactions are the other way around. The reactants have less enthalpy than the products, and in order for the reactants to turn into the products, there has to be a net input in energy equal to the delta H, equal to the change in enthalpy that is needed to form those products. Most reactions require a little bit of energy to get them going. This is what we call the activation energy. If there wasn't an activation energy, these reactions would just happen spontaneously all the time. In fact, they already would have happened. There'd be nothing to stop them from happening. But a little energy wall, a little bit of difficulty to get it going, is normally present in most of these reactions. Now, if we think about combustion, like setting fire to something, you have to strike a match. You have to input a small amount of energy to get the reaction going. Now, what that energy does is it gives the very first atoms enough energy to click together, and in the process that gives off more energy, which can then sustain all the rest of the reactions. You only need to light the match once to make the reaction happen. You don't have to keep lighting the match. You don't have to individually start every single reaction. It is just an initial amount of energy to get the reaction going. So what this looks like on our enthalpy profile diagrams, on the exothermic diagram, there's this little hill coming from the end of the reactants line. The energy has to go up and then come down, and the activation energy is drawn from the reactants line upwards. That is the little extra bit of energy that the match has to provide to set fire to your Bunsen burner. And then it gives off more energy, some of which is used to sustain the reaction, some of which actually goes out and is measurable as the enthalpy change. In an endothermic reaction, they normally require significantly more activation energy, because not only have you got to cover the energy difference between the reactants and the products, you also have to provide more still to make that hill even higher in energy than the products. And then once that point is done, the reaction will then sustain itself. Now, the enthalpy change is dependent on the conditions in which this is occurring. Some situations would have a higher or lower enthalpy change depending on the environment itself. Now, what we're going to do is we're going to fix the environment to make it a static thing so that we can just look at the interaction between the system and this standard environment. Now, whenever we're talking about this standard environment, we use this symbol. It's a circle with a horizontal line through it. It kind of looks like the London Underground symbol, and we use it in superscript after the H. It means that we're measuring the enthalpy change in standard conditions. And to remind you what standard conditions mean, the standard pressure is 100 kilopascals, that's 1 atmosphere, it's the pressure of a room. The standard temperature, 298 Kelvin, that's room temperature, and standard concentration, 1 mole per decimeter cubed. We also stipulate that these chemicals must be in their standard state, which is whatever state that chemical would naturally be in if all the other 3 conditions are met. Now, if we were to display the enthalpy change in a reaction, it would look like this. So we've got the delta H in standard conditions equal to minus 635 kilojoules per mole. This is the number of moles it would take for this single mole of calcium to turn into this single mole of calcium oxide. Now, of course, there are lots of different reactions, and we might find that one reaction is different to another and might in fact require a different change in enthalpy. So we have to be specific about what kind of reaction is causing this change in enthalpy. And one of the very first is if we're forming something, in this case, calcium oxide. What would be the enthalpy change of its formation? Well, we would use the symbol here, delta subscript F, H, superscript, circle, horizontal line. So you can see it at the very bottom there, delta F, H standard. And so that is basically what we've been given above. It is the amount of enthalpy required to have calcium oxidize and form calcium oxide. A different one would be the enthalpy change of combustion. And so here we replace the F with a C. And so it's delta C, H in standard conditions. Now take a look at the formula here. We've got methane burning in oxygen and it's producing carbon dioxide and water. And what we're doing here is we're pedantically looking at how much energy is stored within the bonds of each of these chemicals. The CH4, it's got 4 carbon-hydrogen bonds in total. They are storing an amount of energy minus 74.8. O2, by definition, it doesn't take any energy, so that's 0 kilojoules per mole. And CO2 is minus 393, and water is minus 285. So we now know how much energy is stored up in the reactants and the products. If we want to know the enthalpy change, we need to take the sum of the enthalpies of formation of all of the products and minus the sum of the enthalpies of formation of all the reactants. So basically, products minus reactants. We stick the numbers in, as you can see there, and we come up with that the enthalpy change of combustion of methane is minus 890.3 kilojoules per mole. This is the enthalpy per mole that we get from methane when it's undergoing combustion. Now, we could directly see if this is correct with calorimetry, so basically heating up water and measuring the amount of energy change that has occurred by the combustion of each mole of methane. Another reaction of interest to us is an acid-base neutralisation. Now, when we simplify acids and bases, ultimately what's going on is the same thing. We always have H plus ions being neutralised by hydroxide ions, and they have a reaction together and form water. Now, for every mole of water formed, released is 57 kilojoules per mole of heat energy, so that the enthalpy change of neutralisation for every single mole is 57 kilojoules. Now, this neutralisation reaction occurs whenever any acid neutralises any base, because what they all have in common is that they all have H plus and hydroxide ions. Now, one last thing before we leave this is that this term enthalpy was first used by Dutch physicist Heike Onnes in the early 20th century, and it comes from the Greek word enthalpion, meaning to warm in or to put heat into.